Hello everyone, my name is Qitong Wang. I will be presenting our work, Aokana, a GPU-driven workflow running framework for open world games. We apologize that due to visa and other problems, we are not able to present today in person. In recent years, open world games have been increasingly popular among players. GTA is one of the most famous open world games in the world. Genshin Impact has sparked a wave of interest in open world games on mobile platforms. The recent game Neverneath to Everneath is also highly expected by players. Open world games typically feature large game maps, which require a vast amount of content and artistic resources to populate the game world. However, the large-scale maps typically required for open world games necessitate substantial cost and extensive human resources for asset production. This unaffordable cost deters many low-budget teams and independent game developers from developing open world games. But game players can always come up with workable solutions. How about voxels? Voxel representation of 3D geometry is highly intuitive and structured. Voxel assets or open world maps can be efficiently generated in bulk through randomization of procedural methods. Independent developers have used procedural generation algorithms to quickly create vast voxel maps. As a result, more independent developers are turning their attention to stylized voxel games, such as Minecraft and Teardown. Taking Minecraft as example, where each block is sized at 1 cubic meter, an almost infinite natural environment map can be effectively generated by adding random noises. However, voxel-based approaches also possess some technical challenges. For example, when developers aim to create a large artificial city map, they need to restore the complete map data on disk and selectively load necessary data into both memory and VRAM. Simply use mesh to represent voxel scenes is not always feasible because meshes can occupy a very large amount of VRAM. Loading the entire map into memory at once can create significant memory pressure, easily resulting in out-of-memory errors. If the game requires fine-grained voxel details, the storage cost will further escalate. For open-world games, view distance greatly affects players' experience. Players want to see distant scenery. However, as there are more distant objects than close-by objects, letting the objects in distant scenes is the main consumer of the RAM and VRAM. How to process distant objects with low memory consumption is the main challenge for real-time rendering performance of open-world games. Since distant objects appear smaller, we don't need to maintain all the details. Therefore, we can tailor or customize level of detail systems for voxel games. To wrap up, our goal is in Aokana is to design a rendering framework for open world voxel games that can offer extremely long view distance for large world map, but with high performance rendering and low VRAM usage. We now present our solution, Aokana. So Aokana primarily is composed by three components: sparse voxel DAC, LOD chunk preprocessing for low memory consumption, and word partitioning and thread streaming, as well as GPU-driven voxel rendering pipelines for fast rendering. We first extend sparse voxel DAC SVDAG by using multiple SVDAGs with different levels of details at LODs to represent the entire thing. Sparse voxel DAG is a technique that represents a voxel trunk in a word. It is a data structure obtained by merging isomorphic subtrays of sparse voxel octree, which can greatly compress the geometric information of voxels while still retaining the ability of performing ring matching. Due to the pointer link structure of SVDAG, it is not cache-friendly. As the voxel resolution continues to increase, the depth of the SVDAG also increases, leading to more indirect jumps along the path from the root node to the leaf node, which results in memory access bottlenecks. To reduce number of index jumps, we propose that instead of using a single SV DAG with a large depth, multiple SV DAG with smaller depths should be used to represent the entire thing. To use the multi-SV DAG design, we first divide the entire open working map into a series of actual land cubic regions, each region maintaining a trunk of resolution of 256 to the third voxels, to the other three voxels. For each trunk, employ a sparse voxel DAG for compression and representation. As a result, the entire open world voxel game is segmented into several SV DAGs. Each trunk contains two types of information: geometric information, indicating whether a voxel exists at position X, Y, Z, and color information, which specifies the color of the voxel at that position. We decouple the geometric and color information of the trunk and compress them separately. For the compression of geometric data, we employ a method similar to SVDAG, which involves merging isomorphic subtrays of sparse voxel octotry to form a DAG. A node in a DAG is represented using 8 to 14 bytes. The first 4 bytes of each node child of each node data contains a 32-bit head node, where the lowest 8 bits represent a child mask that indicates the presence of corresponding child nodes. The following 4 bytes store the number of leaf nodes in the subtree rooted at that node. The final 0 to 32 bytes contain pointers to children nodes, which the number of pointers corresponding to the number of binary ones in the child mask. For the 3 deepest layer of nodes, we consider them as individual 4x4x4 leaf chunks and utilize a 64-bit bitmap to represent the geometric information of the leaf trunks. We further decouple color information from geometric information for higher compression ratios. Each node in the SV DAG because the number of leaf nodes in the subtree is at that node. By accumulating the counts of child nodes along the path from the root to the leaf node, we can determine the index of the current leaf node in the DFS order. This index is then used to store the color of the leaf node in a separate and independent color array, which is subsequently compressed. We simply use wrong length encoding to compress the color array due to its high compression ratios on ring marching performance. To further reduce VRAM usage, we implemented a LOD level detail mechanism for the trunks. We consider the smallest voxel trunk, which maintains a resolution of 256 for a region of size 256 to 3 as LOD1. Using a method like octotree, we aggregate 8 LOD1 zero trunks. We aggregate 8 LOD0 trunks into a single LOD1 trunk, which returns the same resolution of 256 to 3. Thus, each voxel in LODN trunk is derived from the aggregation of 8 voxels from the LODN-1 trunks. This process continues recursively until the entire word is aggregated into a trunk. We maintain an implicit octotree on the CPU side, organize the trunks and filter those that need to be loaded. Whether a trunk is influenced by camera changes, we initiate the coroutine to perform a recursive search starting from the root node of the octotree. Each time a node in the octotree is accessed, we first check whether the region it manages contains LOD trunks. If it does not, we continue the recursion downwards. If the current node does contain LOD trunks, we use an error formula to determine whether the current LOD can satisfy the visualization quality requirement. If the LOD error is greater than 0, further subdivision is necessary. If the LOD error is less than 0, the trunk is marked as needing to be loaded. The LOD error formula is based on the position and size of the trunk, as well as the position of the camera. Here, streaming factor is a predefined hyperparameter. A larger streaming factor indicates that distant objects will have more visual details, which correspondingly require more VRAM. This is the trade-off. When determining the loading order of trunks, we can prioritize loading the trunks with the higher LD levels, allowing us to directly remove out-shelled blocks associated with the trunks to free VRAM. When there is sufficient space in the VRAM, trunks that are closer to the players are prioritized for loading. Here is a demo. We also design a GPU-driven rendering pipeline for efficient SVDAC-based voxel rendering. The entire rendering pipeline mainly includes several passes. First, trunk selection pass, then tile selection pass, build high Z pass, and re-marching pass. All these passes are executed in compute shaders. Our custom passes are inserted after the opaque pass, before the transparent pass in the forward rendering pipeline. It can certainly be extended in a deferred rendering pipeline as well. Before all our passes begin, all opaque objects in the scene have already been rendered. We pre-compute the axis-aligned bounding boxes for the portions of each trunk that contain valid voxels. And in the trunk selection passes, we use Frustum counting based on the bounding boxes of the trunks to eliminate those currently not visible to the camera. In the tiling select pass, due to the high cost of re-intersection with trunks represented by SVDAC, we aim to minimize re and trunk intersections to reduce overdraw and ensure rendering efficiency. In the tile section pass, we divide the screen into a series of tiles with 8x8 pixels. For every 4x4 tiles, we allocate a thread group, assigning one thread to each tile. We project screen rays from each tile to determine which trunks that passed the trunk selection passes contribute to the current tile. For the trunk currently occupied by the camera, we perform a ray SVDAC intersection test, while for other trunks, we conduct ray box intersection tests. We use this intersection depth value as a depth value for the current tile, and we perform high Z counting on these tiles. After the tile selection passes, we identify which trunks contribute to the corresponding tiles, so we can ultimately this results in a series of tile trunk pairs. We use a customer tile infrastructure buffer to store the coordinations of each tile that passes the intersection test and the corresponding trunk ID as well. So in the build high Z pass, we construct the high Z texture from the depth information of the current frame's depth texture. Since the camera may be moving at high speeds, using the previous frame's high Z texture for tile counting may not be accurate and can lead to incorrect counting. Therefore, we re-execute the tile selection passes, performing an indirect dispatch compute shader on all tiles that were called in the first tile selection passes. We use the current framework's tile texture to reapply high Z oscillation counting to filter out tiles that are currently incorrectly counted. For all tile trunk pairs filters in the file selection pass, we perform an indirect dispatch compute shader to initiate the DAC ray matching passes, march passes, assigning a thread group to each tile. We use a 64-bit visibility buffer to record visibility information. In this pass, we employ a ray intersection method similar to that in ESVO to calculate the intersection points between each pixel on every tile and the corresponding trunks SVDAC. We use interlock to write depth value, normal information, trunk IDs, and voxel coordinations as intersection points to a 64-bit visibility buffer that matches the size of the screen. In the color resolve bus, we divide the screen into 8x8 tile and allocate a thread group to each tile in the compute shader, assigning one thread to each pixel to compute its color. First, we retrieve the information for this pixel from the visibility buffer. If the information is valid, we extract the normal trunk ID and voxel partition. We then compute the DFS order of the intersection node in the SV deck based on the voxel partition. Using the DFS order, we perform a binary search in the color block array to find the corresponding color block. Finally, we shade based on the norm and color, writing the shading results into a color texture. If using the deferred rendering pipeline, we need to first write this information to the G buffer before proceeding with the subsequent deferred shading process. So we implement Aokana using the render graph API in the Unity 6 game engine with Aokana as a rendering backend to evaluate its effectiveness. We conducted experiments on 3 open world voxel maps, San Miguel, Sposa, and Winfield scenes. Winfield is derived from a popular Minecraft save file. It can represent a real game scene with large-scale modern city, allowing us to evaluate our method's performance in real open-world games. We first compare the storage sizes in things with different resolutions. Our method has a low VRAM usage compared to other approaches. We only need to retain about 2% of the original data in VRAM, while VRAM usage is reduced by up to 9 times compared to hashtag. This image gives a visual comparison of the level details between our approach and the other existing gaming softwares. Our method can better preserve the visual details of distant objects compared to Avoid and Microsoft's Distant Horizon MOD. We then compare the rendering time of our approach and other methods for single frame. The rendering speed of our approach is faster than that of hashtag, achieving a maximum speed up of up to 4.8 times in the testing. And our method rendering speed is less sensitive to screen resolution. We now compare the time to compute primary ray intersection points. Our method has advantages in high-resolution scenes in real open-world scenes, achieving a maximum speed up of up to twice of hashtag in testing. We now present a final demo of an open-world exploration using Aokana. Basically, Aokana can enable players to run seamlessly through the open-world maps while maintaining high quality within full distance scenery. To conclude, in this paper, we propose Aokana for real-time rendering of large-scale voxels in open-world voxel games. It incorporates a level details mechanism and a staging system, enabling seamless map loading as players traverse open-world game environment. We also designed a corresponding high-speed GPU-driven voxel rendering pipeline to support real-time rendering of the voxel things that contain tens of billions of voxels. Aokana can be directly applied to existing game engines and easily integrated with mesh-based rendering approaches. In our future work, we plan to support voxel rendering with various material models. We also plan to better integrate Aokana with traditional mesh-based approaches to seamlessly support mesh-based collision detection, navigation system, and other modules. Thank you very much for your attention. We apologize again for not being able to present in person today. So if you have any questions, please feel free to drop us an email. Thank you so much.